Good afternoon, everyone. I am William. This is Ohm, Faith, and Kate. Together we form the Microsoft Capstone Group. For the past 4.5 months, we've been hard at work on a solution to a vexatious problem that farmers often face. That being how to make sense of the large sets of data that they call from many sensors and GPS location devices that are on their farm implements. So we've developed a data pipeline that involves GIS applications, Power BI visualization tool, as well as Microsoft Azure Cloud Computing Platform to build visuals and predictive models on the yield that farmers have. So, we first confronted with a large CSV file that contains many different metrics like the current yield that is going through a combine, soil moisture, as well as the geospatial location of the combine within the farm field. And large CSV files are ugly. We can have as many sensors on a combine as we would like, but it means nothing unless we can take this data and do something with it that the farmer can use to better inform their business decisions. So, this is our process here. With the data, we first have to clean and prep it. It contains a lot of errors inside of it. Also, we have to make it to a format that we can perform visuals on. Then we supplemented all the data we received from the combine with climate data. And then we use this augmented data set to train statistical models in Azure's machine learning service.
So our first step was data prep. We had to clean it because it wasn't usable in the form it was in. So the data we had was the data collected during harvest. It was combine records of the current yield, the soil moisture, and the coordinates. It was stored in ESRI shapefiles, which allowed the GIS programs to render it into this map that you see up here.
So our process of cleaning the data, the instruments that the combines use and geographics can kind of cause irregular data. So we had to fix that by taking the plus and minus 3 standard deviations, and that gives us the upper and lower bounds of the yields. And then any yields that were outside that upper and lower bounds, we just removed them. And then we did this for every harvest year. And if we didn't do that, we would get a lot of bad data. So for prepping the data, it was divided, the field was divided in 20 by 20 meter squares. And in each tiny little square, we recorded the sum and mean, and then we bin the data accordingly. And then to normalize the data, we want to determine the maximum yield after binning the data. And we do that by dividing each bin's yield by the found maximum yield. And so each bin's yield is now a percentage of that yield's maximum yield. And so normalizing the data is important because each year has different crops, weight, and etc. So it's hard to compare them. So after normalizing, it lets us compare the data at the same level of meaningfulness.
So in addition to the data we have coming from the combine, we collected data from NDOM to see if we can tie it with the yield values. But the level of granularity that we chose, that we were able to collect was not enough to pick up on that pattern. So in the end, it was not useful, but we made an effort to integrate weather data into the data set. So these are the 3 things that I collected. We collected from website. So first one is average temperature for the day. So we broke down the life cycle of the plant into 3 stages: vegetative, reproductive, and mature, and calculated the average temperature in those periods and average total precipitation as well for those periods, and added in as an extra column to the data set. So those are the weather attributes we try to add to the data.
All right, so our third step after we augmented our data set was to actually visualize the data. So yeah, again, large CSV files are ugly, and you can't just look at it and come up with certain conclusions. So we use Microsoft's Power BI visualization tool to develop these visualizations. So there's 2 routes we could take when we're developing these visuals. One would be performing statistical analysis on the data, and then visualizing that. So this is the one I'll describe here. We used a box and whisker plot after we performed this statistical analysis on the data, because box and whisker plots are nice. Conveys a lot of information in a very friendly format. So yep, we took all of the range of the elevation found throughout the field and divided it into 3 equal intervals, and then assign the lowest interval to be the low category, middle to be middle category, and the high to be the high category. And then using those categories, we were able to develop this visualization right here. So here we have the yield by elevation category. The yield's normalized. So if you look at the top, we have the maximum equals exactly 1. That does that by design. But there's some interesting conclusions we can draw from this. So clearly the high category has the largest partition of the yield, and also it seemed to have the most yield as well. So in addition to the elevation visual, we also performed statistics on the precipitation and its relationship to yield. So precipitation was divided into 3 categories: precipitation during the vegetative portion of the plant's lifespan, then the reproductive stage, as well as the maturity stage. And then the precipitation was further divided into 3 more categories: low, mid, high. Pretty much the same method we did with the elevation. Came up with these visuals right here. Now this is precipitation during the vegetative stage. Now notice high precipitation during this portion of the plant's lifespan corresponds to generally a higher yield. But if we move on to the reproductive stage, we notice that the higher yields tend to be associated with mid-level amount of precipitation. And then if we move on to the mature stage here, clearly the low precipitation category is associated with higher yield. So that's kind of a neat conclusion. Probably nothing that the farmer doesn't already know, but we can easily use different metrics and use Power BI to develop, make conclusions similar to this. Pass it off to Om here.
So this is one of the takeaways here. From the standpoint of farmer, you can use ArcGIS to identify the bad patches in the farm by looking at all the data coming from different years. So this is what Power BI visual looks like. It does the same thing, but it doesn't have that color coding, and it doesn't allow me to control the limits that we set for the range. So in the manual mode, so these are the 2 contrasting visuals.
So this is the visual me and Kate worked on. It's a representation of the field, and The red squares are where the mean yield is lowest, and the greens where the yield is best. And you can filter it based on year, so you can switch the years of the field, and I'll tell you the total yield value up on top as well.
So step 4, after we developed these visuals, we took the data and see what we could do with machine learning, see what sort of models we can train and develop.
So within this machine learning studio, we took 15 years of past data to predict the next year's harvest yields. And Studio is fairly easy and simple to use. You just drag and drop things to create the model. And we have a diagram of that in the next slide. It's best for data science novices as it doesn't require any coding at all. But however, there are some trade-offs. Like one example is it doesn't use hyperparameters, which the service does. And that's just a visual of our machine learning service studio model.
So that how this previous model works is we imported the data set that we got from the field, and then we cleaned the missing data with the standard 3 standard deviations. We split the data into test and training set, and we trained the training set with linear regression, scored the training set against the test set, and exported new data as CSV file.
So in addition to the Machine Learning Studio, Azure also has the Machine Learning Service. It's a little bit more robust than Studio. The screenshot you saw is what the user sees in Studio. Very simple and easy to use. However, you're going to need to know a little bit about coding and the Azure Python library to be able to use the service. So you can use any Python IDE with it. Jupyter Notebooks is probably the easiest. So one notable divergence between Service and Studio is that Service has a library titled AutoML. So essentially machine learning iterates through this algorithm that determines how to adjust the parameters of the model we're trying to train. However, there's all sorts of different algorithms we can use to train the model. In Studio, we would have to try out every single algorithm on our own and do it manually, and that's a lot of work. However, Machine Learning Service provides this nifty library for us to iterate through all these different algorithms automatically. That's what we use for our machine learning work. So, pass this off again to Om.
So, from the perspective of farmer, he can consume these models that we built from the Excel. So he can just install an extension called AML, and it allows them to predict from Excel. So they just need to punch in the causal factors, and it will predict the Y. So we did it via ML Studio, and we are still fixing the ML service part. So it can be done from both ML service and ML Studio. So yeah, for him, I mean, that's the one of the useful things. Yeah. So while setting up the dev environment, we had a lot of trouble because there is no straightforward documentation on how to do it. There were so many errors. That was one of the main problems we faced. And then when it comes to the explainability package, like they didn't, that package doesn't allow us to choose the level of granularity when it comes to when ranking out the importance among the attributes. It talks in terms of feature values, not in terms of features, like soil type. That's the information farmer wants to know. But it directly gets into the values, the combination of values. So that's one of the problems we encountered.
So our deliverables for this project were we made Power BI templates, Microsoft Tools documentation, and an outline of GIS application steps for graphing our data that you saw today. And we just want to give you a thank you to our mentors for all the help. That's it.
Does anyone have any questions?
Sure. Is there any ability for a system like this, rather than just taking, well, here's all the previous years, to do something as a year is progressing and you're getting a little bit of information, like, oh, we've had this much rain so far, to start feeding that in to get a general sense of what's the range of possibilities in terms of yield? If I wanted to start investing in features, or maybe I want to take out more insurance to potentially cover liability, things like that might be helpful as well.
That's certainly a possibility. So we were only given the data that was culled from the combine during the actual harvest, so no interim data between planting and the actual harvest. But I wouldn't see any reason why we couldn't just iterate this pipeline every time we get more data. We might be able to update the machine learning models to for something like that, but it's definitely a possibility.
So to summarize, I mean, you are talking about the situation where we have partial information for causal factors. So there is no way to fill in the gap except for guessing for the rest of the information. So we need to make a guess there for the rest of the information. So but we can use whatever we have, and we can get an idea of where it is heading yield-wise.
So the climate data would be an example. We couldn't really do anything with yield because you don't harvest
Yeah,
anything, but
our model was not able to pick up on weather attributes because it doesn't have enough granularity to remember in symbolic knowledge. So, sorry, non-symbolic.
Is there a plan to start incorporating some of the information from satellites or drones?
Weather kits is the first place that we want to start if we're gonna do it. Paolo mentioned about weather kits collecting data in the individual farm. So that's more.
You know, weather's different.
so that's not a route we've explored.
We didn't do anything with computer vision in this problem. Like when you say images coming from
NDI.
Yeah, exactly. We didn't incorporate. I mean, it could be a different approach, I guess, to the problem.
I know the ag guys are doing a lot of that.
Yeah,
Thought it would fit in at some point.
yeah. This is straight data based. It doesn't involve any computer vision component.
Yeah, I'm sure it'd be useful for like a lot of fields or multiple fields, but we only had the one field, so it was pretty simple. Just put it in there. Yes.
Can you summarize the results you got from your ML work, both for studio and service? Were you able to come up with reasonable predictions or not? Which algorithms would be? I mean, I know you've done regression on the studio side. What data would now come up? Just talk a little bit more about that process.
So I believe we got up to 98% accuracy when we were testing it. However, we weren't able to really. So there's some problems with the ML models we developed. So it incorporates a geospatial variable. So it's, you can't really use the field you can't use the model for anything but that specific field. But in addition to that, if we were to go ahead and predict fields, we would have to format the CSV file and feed the model it, and we'd have to make sure that every grid box that had training data had a corresponding grid box in the X values we were feeding it. So we weren't able to get actual predicted values. It's the long story.
So to summarize it, we are getting more accuracy because of mean being the response variable. On ML service side, we got 90% accuracy with an ensemble method, ensemble decision tree. So the
Were you treating it as a classification problem or regression problem?
Still regression. The range is so small, 0 to 1. That's another problem of normalization. There is only so much space to do the guesswork. That's another cause contributing to that high accuracy, even though it's a regression problem. So we are planning to use these sums instead of means and give it a shot, so that would be a real useful thing to follow, like to say, to guess how much it's gonna be per acre, total yield. So to summarize, we got high accuracy because of mean and short range, and yeah.
And we've written up some documentation discussing the differences, and then we'll send that to you on Friday.
And we automated the workflow from bottom to top, so even including an ArcGIS. So
Any other questions? All right, thank you.